Hello and welcome to the first lesson of Unit 3 on Substitution and Elimination. So a quick word before I start this lesson. Unit 3 is about analyzing systems of equations. In particular, we're going to be looking at linear equations, as you could kind of maybe see the examples down here below. This is covered in Algebra 1. In fact, a lot of this lesson applies to Algebra 1. You've done these techniques before, you've worked with systems before, but in Algebra 2 we kind of bump up the difficulty, right? You'll find that right now we're working with two-dimensional systems, meaning x and y. We only have a square plane here, right? A flat plane. We will talk about three-dimensional coordinates. We've got x, y, and z. So we will get to three-dimensional systems. Now, a system of equations is essentially what the goal is you're trying to find values for the variables in that system where all equations are true. Meaning, so example, right, if I find this coordinate 3, 1, I want it to be true for this equation and this equation, right? Or maybe I have a three-dimensional system like 1, 2, 3, and I want this solution to be true. I want these values for x, y, z to work for all three equations in the system, yeah? And so that's kind of what the goal is. So anyway, this lesson is about substitution and elimination. But before I get to that, we did do a quick review on graphing systems. This is about the only time we're really going to do that until we hit inequalities, where we'll start graphing again. But this is just very quick Algebra 1 review, and I'm just going to kind of fly through this because it's more or less a warm-up. Okay, so this is a review on graphing. What we're going to do is I have linear equations here that I can graph, and they are in slope-intercept form, y equals mx plus b, so we're going to do that. I look at the first equation here. I see that y equals 2/5 x minus 3. That tells me I have a y-intercept at 3, and the slope is 2/5, so the rise over run is up 2 over 5. Wow, that's pretty big. I guess that's it. I just need those 2 points, so I'm going to draw a straight line through them, like so. I have this first line. I'll switch colors here, just so we can really see the other line here. Now the next line is negative x plus 4, which means a y-intercept of 4, and a slope of negative 1, which means down 1 over 1. Down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1. Right? All the way, so like this. And so I'm going to draw a straight line, if it will straighten out. Thank goodness that my iPad does this. And I have my 2 points of intersection, right? So you'll notice that they meet at this common point here, which is at 5, negative 1. 5, negative 1 is the solution to this system of equations, yeah? Because when you substitute x equals 5, you get y equals negative 1 for both equations. Now, I'm not going to do that because it's going to take some time, but if you'd like to verify for yourself, plug in 5 here, and you will get negative 1 for both outputs. Okay. The next two are just, again, warm-up questions to kind of jog your memory, but I will go through it in case you want the quick recap. If you want to skip this, scroll ahead through the video. It's no problem. I'm going to graph these next two here. So the red is going to be y equals 2x minus 4. That's a y-intercept at negative 4 with a slope of 2. So I'm going to just kind of nicely and neatly make these little lines like so. Say boop. Pretty nice. And then with the blue line, what I'm going to do is I'd like to graph this using y equals mx plus b. So let me solve for y real quick. I'll add y to both sides. I'll also add 3 to both sides. And I'm going to get 2x plus 3 equals y. And so that tells me my y-intercept is at 3 with a slope of 2. Yeah, I guess so. Slope of 2. Sorry, I guess I just had a little bit of a brain fart right there. I was like, huh? I was like, I'm fine. We are fine. This was expected to happen. And there we go. I have two lines like this. You'll notice that these two lines are both parallel, right? Both these lines are parallel. Therefore, there are no solutions. Meaning, right, so these two lines do not intersect, so there's not a solution to this system of equations, meaning there does not exist an x and y coordinate that satisfies both equations simultaneously. Sometimes they call these simultaneous equations. So systems of equations or simultaneous equations. I think they call that a lot like Europe and stuff. I'm not sure. I didn't grow up in Europe, but I think that's what I've heard. And I'll try this last one here. 3x plus y equals 6. Do keep in mind, you don't have to put it in slope-intercept form. You could find points if you like, right? Because I know that 1, 3 will be a point because 3 times 1 plus 3 is 6. So I know that's a point that's going to work. I could also do like -1 and 9, I guess. But whatever. It's just doesn't matter. I'm just going to do it the way you guys know, which is to solve for y, which is y equals, I'm going to subtract 3x here. So -3x plus 6. So that'll be up here. Oh, and look, it's just like I said, right? Down 1, 2, 3 over 1. That's the slope. So yeah, that point I found does actually work. And I'm going to connect this line like so. If it will straighten out. Beautiful. And now I will do blue. This is chewing up some video time, but it's okay. We're being casual, right? We don't care. We're just having fun. 2y equals the -6x plus 12. And if you notice, I can divide by 2 to isolate y. So y equals -3x plus 6. Oh my gosh, that's the same line. So all these points are the same. And I'll draw my little thingy, a little graph like so. Boom. Yeah, they are the same line. So these lines are overlapping. Or you could say they're the same line. Therefore, there's an infinite amount of pairings, right? X comma y, there's an infinite amount of points on these that work, so there are infinite solutions. Infinite solutions. Anyway, we do this quick little review on graphing because it's a quick reminder that when you work with systems of linear, that is, just strictly linear, don't venture too far out from there. With linear, you're either going to have one intersection point, one solution, no solutions, parallel lines, or overlapping lines, infinite solutions, okay? And this concept does carry over if you extend this to planes. So if you have a plane here and a plane here, and then, I don't know, another plane this way. Don't worry about that. I'll show you a visual later. But when you get into 3D, when you do work with x, comma, y, comma, z, this carries over. So one solution, no solutions, infinite solutions. Okay, so now let's do review of substitution method. And I'm going to be pretty quick with this. Or maybe not. I don't know. I talk pretty slow in these videos. So in mathematics, what is substitution? What does this word mean? Well, to substitute something means to replace, right? So a substitution is a sort of replacement of some mathematical variable, right? So replacing a variable with another mathematical expression. And I will stipulate, it doesn't have to just be a variable. It can be any mathematical expression. Maybe here's a quick example. 2 plus x plus y, in parentheses, equals 4. And x plus y equals 2. So then, or maybe I said I didn't know what this was. 2 plus x plus y equals question mark. But x plus y equals 2 means I can replace x plus y with 2 and find 4. Does that make sense? Whatever. Let me illustrate the idea of substitution here. So, example 1, solve the system using substitution methods. Now, I do have some general steps below, but the essential premise of substitution in the vein of systems is you want to isolate a variable. So isolate a variable. This gives you a mathematical expression for that variable, and then you replace that variable with that mathematical expression. And that's the basic concept. There's really not much more to it than that. It's isolating and replacing. That's the idea of substitution. So the only thing you got to do with systems is figure out what do you want to isolate. And you have a choice here. In fact, you have 4 choices. I can work with the first equation, or I could work with the second equation. And in both equations, I have 2 variables, x or y. So pick an equation and pick a variable. It does not matter which. You have total freedom here. I will note that often variables with a coefficient of 1, right? If I have 1 times x, which just looks like x. Variables with a coefficient of 1 means you never have to divide by anything, right? So for example, see this 3x here, right? 3x plus, if I want to isolate this, I'm eventually going to have to divide by 3. So I might look for variables with a coefficient of 1 because those are going to be more efficient. I'm going to avoid fractions and such like that, right? So I'll notice that y here has a coefficient of 1, so it's probably going to be the easiest one to isolate. In fact, indeed, it follows that if I just subtract 1/2 x from both sides, I get y equals negative 1/2 x plus 4, right? And so this is an isolated expression for y. Now what I will do with this is I'm going to take this y here and I'm going to replace it in this equation. So you have 3x minus 2y equals 16, but this y is this thing, right? It's this expression I'm highlighting right here, negative 1/2 x plus 4. And so what you're going to do is replace y with this expression. And you will want to use parentheses here because the expression is taking the place of y, and 2 is multiplying y, which means 2 is going to distribute to everything. So that looks like 3x minus 2, which will distribute to the expression negative 1/2 x plus 4. And this is set equal to 16. Now you'll notice what kind of gets accomplished here. You've put y in terms of x, and then you took an equation with x and y and replaced y with an expression in regards of x. What happens is I have a single expression with only one type of variable, x. And since it's an equation with a single variable, especially because it's linear, it's very easy to figure out what that variable is. So let's distribute this negative 2. I get 3x plus 2 times, let's see, negative 2 times negative 1/2 is 1x. And then negative 2 times 4 is negative 8. And this is set equal to 16. I'll do the classic combine like terms, right? I'm going to get 4x, and I'm going to add 8 to both sides so that I get equal to 24. And then I'll divide both sides by 4, getting me x equals 6. And that's it, right? No, we're not done. Remember, with a system, you are looking for, if I'll show you up here, where's my laser? There's my laser. You're looking for a point, right? 5 comma some, right? 5 comma negative 1 is the solution. So we found the x value, but what is y, right? What point satisfies both equations? So how do we do that? Well, I'm going to take x equals 6 and substitute it back into the expression for y. You see, y equals negative 1/2 x plus 4. So if I replace x with 6, negative 1/2 times 6, well, then I get negative 3 plus 4, which is 1. So y equals 1. means the solution to this equation is 6, 1. And we are done. We are done. Good. That's it. So, and by the way, box your answer, please, so I know that you are done, right? And write it as an ordered pair. It's very standard practice to do that, ordered pair. If you do letters that aren't X, Y, Z, like maybe you have ABC, you could write that like ABC equals a 1, 2, 3. Something like, right? You could just state what the triplet is. Okay. We're going to work example 2, which from class is just student practice. So actually I gave this to you guys, but I'm going to cover it in the video anyway. My recommendation is if you're watching this from home for the first time, to pause the video and try this on your own, okay? Solve this system using substitution methods. So pause the video if you want to try that. I'm going to go over the answer now. And I'm going to switch to blue. So we're going to still focus on substitution. We're going to talk about the other technique in a second. And those of you who know the other technique are going to be frustrated with this, saying, there's an easier way to do it. And I know that. So anyway, we need to pick a variable, right? So pick a variable to isolate. We have x, y, x, and y. And I say, well, they all have coefficients that aren't 1. That sucks. So what should I do, right? How can I go about this? I'm just going to pick one. I'm going to pick the second equation, and I'm going to pick to isolate y. That's just my choice. You may choose any one of these. It is fine. It is perfectly okay. So I will go, I'm going to take this equation, and let's isolate y. So let's add 4y to both sides and subtract 6 from both sides. I get 3x minus 6 is 4y. And then I will divide by 4 to isolate y. So I'm going to divide by 4 here, which means you divide by 4, means you divide by 4 here. And so I get y equals 3/4 x minus 6/4, which actually simplifies to 3/2. Now I'll take this expression and replace it with the other y in the other equation. Quick note, a little star here, don't replace y with what you solve. So if you use the bottom equation, don't substitute it back in there. That's called circular reasoning. You will find yourself going in a circle and accomplishing nothing. I say, you are here. You are here. And your journey looks like this. And then you just keep doing this. So please, please, please don't plug it back in there. Use the other equation, okay? If you say, why are you going in a circle, Mr. Spake? How about you plug it in and see for yourself? And then you'll see why that is a circular reason. Okay. My foot hurts. 9x, you say, I don't care, Mr. Spake. Teach me the lesson. 9x plus 4y equals 2. I'm going to substitute y with this expression here. So 9x plus 4 times, and remember, I got to replace y with an entire expression, so use parentheses, 3/4 x minus 3/2, and this equals 2. Now, I'll distribute the 4, right? 9x plus 4 times 3/4, that's just 3x. And then 4 times negative 3/2 should be negative 6. And this is set equal to 2. So 9 plus 3x is 12x. I'll add 6 to both sides, and this gets me 8. From here, I will divide by 12, giving me 8/12, so that simplifies to 2/3. Fantastic. I love it. I love it. Now what? Well, x is 2/3, and that can be substituted back into the expression for y. So y equals 3/4 times x, but x is 2/3 minus 3/2. And you'll notice that, so you get 3 times 2 is 6, over 4 times 3 is 12, right? 6 over 12, which is 1/2. You could also see that the factors cancel out. 3 cancels with 3, and so then you're left with 2/4, so that becomes 1 over 2. So either way, you're going to get a half, right? However you like to approach that. 1/2 minus 3/2. Well, 1 minus 3 is -2. So that's -2 over 2, which is just -1. So y equals -1. That means my solution is 2/3, -1. And that ordered pair makes both equations true. Yeah? Both that choice for x and y make both equations equal what they say they do. All right. And that's that. So that's substitution illustrated. I don't know. It's from Algebra 1. If you were strong in Algebra 1, you already know this. If you weren't, it's okay. Here we are, right? We're learning. And this is our opportunity to master this skill if we didn't have it before, and that's good. That's why we revisit this stuff. It's useful. And so, yeah, you can see the general principles, the general steps for substitution down there. You're welcome to read that, but I'm not going to here. Okay? Let's move on. I don't want to talk all night here. Okay, review of the elimination method. Did I capitalize that? No, I didn't. I did. Review of substitution method. I capitalized those. And now, over here, I did not capitalize E and M. That's it. I am sad. I say it. No, I am sad. Okay. Mr. Spake really likes his stuff to be perfect. Okay. The method of elimination is a process of identifying what's called an additive inverse, which will eliminate one or more unknowns from an equation. So here's the goal, right? You want to get a single variable alone, a single variable to be solved. Then you will substitute the solution and solve for the rest. And I'm going to model what that looks like with example 1. Real quick, you might be asking, what the heck is an additive inverse, right? Well, definition, an additive inverse is what you add to an expression to make it equal to 0. I could go really in depth about the word identity. I'm not going to do that. But an additive inverse is, if I have 5, what do you add to 5, right? What do you add to 5, to get 0? Well, -5, right? So the additive inverse of x is -x. If I have -3, that's a terrible 3. If I have a -3, the additive inverse is 3. Done. Yeah, that's the basic premise. So let's look at example 1 here. And you'll notice that example 1 is example 2 from the previous page. Oh my gosh, look at that. It's this. We just did this. So we already know the answer, right? But look at how elimination works. And this is what I asked the class. I asked the class this. Do you agree that 2 plus 3 is 5? And you would say, yes, Mr. Spake. I agree that 2 plus 3 is 5. And then I would say, do you agree that 1 plus 1 is 2? And then you would say, yes, Mr. Spake. I agree that 1 plus 1 is 2. And then I would ask, would you agree that if I add the left side of the equation, I have 2 plus 3 plus 1 plus 1, and if I add the right side of the equation, I get 5 plus 2. And to this, I would say 2 plus 3 plus 1 plus 1 is 7, and 5 plus 2 is 7. So would you agree that this equality stands, right? If I take the left side of an equation, and I add that with the left side of another equation, and then I take the corresponding right sides and I add them together, their sums are equal to one another, right? This is a sort of principle of adding equations. And you would say, I agree. You'd say, yes. I'd say, happy. Now, if you agree that you can do that, then you agree I can take these two equations and add them. And I'll notice that 9x plus 3x is 12x. And I'll notice that 4y and negative 4y create what's called a zero pair, meaning they're additive inverses, right? 4y minus 4y is 0. They are gone. And then on the right side, 2 plus 6 is 8. Oh my gosh! Divide both sides by 12, x equals 2/3. Whoa, look at that. Look how much work that was compared to all that. Oh my gosh. Having to do this with the fractions and the combining the like term. No. Look how much faster that was. Yeah? So an elimination is a useful technique. And of course, what we can do from here is you can take x equals 2/3, plug it back in, right? I could plug it in 3x minus 4y equals 6. So this is like 3 times 2/3 minus 4y equals 6. That's 2 minus 4y equals 6. That's negative 4y equals 4. So y equals negative 1, right? And you could use substitution to solve it like that. If you want to slow down the video and process what I just did there, all I did was I took x equals 2/3 and I put it back into this equation right here, and I solved for y, right? I do want you to notice, though, I could, if I so choose, use elimination again. So actually, I'm going to kind of clear this up. I'll keep that work there. And instead in blue here, notice, so what I did was I added 4y with negative 4y because they sum to 0. But suppose I chose x as a variable to eliminate. How could I go about doing that? Well, I'm going to ask you the Socratic method again. Would you agree that 1 plus 2 equals 3? And you would say, yes, Mr. Spick, I would agree with this. And then I would say, if I multiply both sides by 4, would you agree that 4 distributing here is 4 plus 8, and 3 times 4 is 12, which is true? And you would say, yes, Mr. Spake, I agree with this statement. And I'd say, okay, so we can multiply equations, and as long as we carry through that multiplication, they still hold their equality. Yeah, they still remain balanced, right? So observe 9x. What could you pair with 9x? 9x plus what equals 0? Well, negative 9x. But what do you have beneath it? You have a 3x. So I ask you, how could I change a 3x into a negative 9x? What could I do? Well, I could multiply by negative 3. And if I multiply by negative 3, then that creates the opposite of 9x, which is going to create my 0 pair. So what I'm going to do is I'm going to take this equation and I'm going to multiply by negative 3. And watch what happens. Do be sure that you distribute this negative 3 to all terms. I'm going to get 3x times negative 3 is negative 9x. Negative 4y times negative 3 is positive 12y. And 6 times negative 3 is negative 18. And then I'll just copy the equation above it, like so. Now, if I draw a bar and add, you'll see that 9x and negative 9x cancel, which is to mean they are additive inverses that sum to 0. And 4y plus 12y is 16y. 2 minus 18, or rather 2 plus negative 18, since we're going to be particular, is negative 16. And then I will divide both sides by 16, netting me y equals negative 1. Which we already knew, right? I say, yeah, we already knew that from the previous problem and from just substituting 2/3. But I'm doing this to illustrate to you how elimination can be used in two instances, right? This first instance, the additive inverse was already present, right? 4y and negative 4y, we already had that. Just add them together. But suppose the additive inverse is not, like 9x and 3x. You can use multiplication, they call it scalar, multiplication to sort of alter the equation to be something else that's also true, it's equivalent, and then use that to make a zero pair and eliminate a variable of your choosing. Okay? Okay. So now, honestly, that's pretty much the video. The next two examples this is student practice, so I handed that in class for people to try. And then example 3 is a student exploration. So my recommendation is that you pause the video and just go from here. Try example 2 on your own, and then try example 3 on your own. But if you would like to view me walking through these, I will go ahead and do so as part of this video. But if you get the premise, you remember substitution elimination, then take it easy. Go have a snack or something. Yeah, take a break, and you're good to go. Okay, so I'm going to work example 2 now. Again, you're welcome to pause the video and work through this. Now, I have a task. I want to eliminate a variable. And I say to myself, well, I've got 1/2 x and I've got 4x. So I could try to make these match somehow. I also have 5y and negative 9y. Sorry, I'm yawning. I'm taking a quick yawn break. I need to make an additive inverse out of one of these. I'll notice that, well, 1/2 plays a little bit nicer with 4 because, if I multiply 1/2 times 2, it becomes 1, and that's pretty nice, right? Whereas 5 and 9 are both prime. I guess you could say that they're co-prime too, because they don't share any common factors, right? I'm sorry, I misspoke. Mr. Spake, 9 is not prime. 9 is 3 times 3. That is not prime. But I still think they're called co-prime. So 5 and 9 are co-prime, meaning they don't have any factors between them. Whatever. Who cares what I'm talking about right now? Just pick a variable, okay? Just pick something. I'm going to pick x. That's what I'm choosing. Now, can I multiply 1/2 x in such a way that it becomes the additive inverse of 4x, right? Because you ask yourself, 4x plus what is 0? Well, negative 4x. So what would you multiply 1/2 x by to get that? You'd say, oh, negative 8, right? Because half of negative 8 is negative 4. So I'm going to take the first equation on the top, and I'm going to multiply by negative 8. And I make sure I carry this distribution to all terms in the equation. Negative 8 times 1/2 x is negative 4x. Negative 8 times 5y is negative 40y. And negative 8 times 7 is 56. Below, I will copy the equation down. That's the second equation beneath. And sum them, add them together. I have a 0 pair with the x's. They are additive inverses that sum to 0. And then I combine like terms here. Negative 49y equals 98. So I will divide both sides by negative 49 now. And I get y equals negative 2. Beautiful. Look at that. Oh, that's great. And so now, what shall I do? Well, I could choose to do elimination again and try to get the y's, right? I could choose to eliminate y, and then I could find x that way. Or I could substitute y equals 2. I think substitution with y equals 2 will be a simpler process. I'm going to use the top equation, 1/2 x plus 5y equals negative 7. That comes from right here. And I'm just going to substitute y with the value I found, negative 2. So 1/2 x plus 5 times negative 2 is negative 7. That's just negative 10. So I'm going to add 10 to both sides. And I get that 1/2 x equals negative 7 plus 10 is 3. And then I will multiply both sides by 2, so because 2 times 1/2 is 1. And then so it's multiply here, so I get x equals 6. Thus, the solution to this equation is 6 comma negative 1. Ha! That's so nice. I love it. All right. We're doing great. one more example to end the video. I will upload, they're not currently uploaded, they'll probably be uploaded soon though. I will upload some more examples of complicated questions. Right now, that was all of those. I mean, every single one of those was an Algebra 1 problem. This is Algebra 2. We are now moving on to Algebra 2, but the concepts is the same, right? You still do substitution, you still do elimination, but you have to do more, right? There's more algebraic steps involved, and you have to think a little bit more critically about what you're doing. Because what we're going to do in this class is 3x3 systems, which means x, y, z. So that's 3 equations with 3 variables, and we're going to figure out how to manipulate those. So again, this is a student exploration. I do recommend you pause the video and try out this problem here, but I'm going to go ahead and work through it with you and just give a sort of step-by-step explanation of how to approach this. So, example 3. Solve the system using either substitution or elimination methods. That was me yawning. And I'm actually going to take a quick sip of water. That was refreshing. All right. Let us continue. Solve the system using substitution and or elimination methods. So you'll notice here that I now have 3 equations. And in the first line, I have 1, 2, 3 variables. In the second and third lines, I have x and y, x and y. That's actually very good. This is very nice. It might look a little intimidating with all the variables and coefficients, and now you have 3 equations and such, right? But the fact that you have a system of 2 equations with 2 of the same variables means you can still use the exact same techniques in the same way that we've been doing it. Essentially what I'm saying is this equation up top is complicated. It has 1, 2, 3 unknowns. But the other 2, not only do they only have 2 unknowns, but they're the same unknowns, x and y, x and y. I will let you know that this strategy I'm about to illustrate to you doesn't quite work as well if it's x and y and x and z. So you'll have to choose a different approach on such a problem. But anyway, since this is a sort of, it's like a subsystem, I guess. I'm just looking at a subset, right? These 2 of these equations. I'm just going to use elimination on this. And I'll find x and y as if it was a normal problem. Because look, if I just black this out, if I just black that equation out, and I handed you this, it's no different from the equations we just did, right? No different. And so let's solve this. So choose a variable. I could choose x or I could choose y. I will choose x. Now, I've got 2x and I've got negative 3x, and I need to make them in such a way that they are additive inverses, right? So how could I do that? Well, one approach would be if I cut this in half, I'll get x, and if I cut this in 1/3, I'd get negative x, and those would add together and get 0. I might avoid this, though, because then I'll have 19 halves and 14 thirds. And I say, blech. I say, no, thank you. I don't really want to do that. So let me choose a different approach. I could instead multiply by 3 on the first one to get 6x, and multiply by 2 on the bottom to get negative 6x. And if I do that, then they will sum to 0. So that's the approach I'm going to choose. I'm going to take the middle equation and multiply by 3. And I'm going to take the bottom equation and multiply by 2. So let's do the middle equation first. 2x times 3 is 6x, plus 3y times 3 is 9y. 19 times 3. Well, I suppose 19 times 3 is simply 3 less than 20 times 3. So that would be 57. And then negative 3x times 2 is negative 6x. And 4y times 2 is 8y. And 14 times 2 is 28. And then I will add these together. And I will notice something magic happen. The x's are eliminated. The y's combine to be 17y equals 57 plus 28. Is that 35? Hold on. I say hold steadfast, matey. Is that right? That doesn't seem right. My brain is 30. What am I doing? Mr. Spake, did you really say 35? I meant 85. Is 85 divisible by 17? I think it is. Well, 10 times 17 is 170. And half of 160 is 80. So half of 170 is 85. So 5 times 17 is 85. Yes, 17 is 5. Yeah, 85 divided by 17 is 5. Cool. So I found y. Now let's find x. So 2x plus 3y equals 19. This was just taken from the middle equation right here. No manipulation. I'll substitute y equals 5. That's 3 times 5. So that's 2x plus 15 is 19. We will subtract 15 from both sides to get 2x equals 4. Then we will divide both sides by 2 to get x equals 2. Fantastic. We are making great progress. X is 2, y is 5. And the equation at the very top is 4x minus 3y minus 2z equals, was it 1? Negative 1. But don't I know x and y, right? I know these things. So 4 times 2, right, minus 3 times 5 minus 2 times z is negative 1. So that is 8 minus 15 minus 2z equals negative 1. 8 minus 15 is negative 7. Yeah. Took a second there. Add 7 to both sides. I get negative 2z is 6. Divide by negative 2. 6 divided by negative 2 gets me z equals negative 3. Ta-da! Hooray! So x is 2, y is 5, z is negative 3. And congratulations. We are happy. We say, oh yeah. We say, oh yeah. We did it. And that's the solution. Okay? Wonderful. Absolutely wonderful. Do notice I write this as an ordered triplet x, y, z. Okay? That's a common way to write three-dimensional coordinates, x comma y, then so is x, y, x, y, z. Okay? And that is the video. This covers the basic premise of substitution and elimination. Yeah? I hope you enjoyed this. This was a nice, solid video. It's good. It's good stuff. So anyway, look out for a video on more complicated ones. I will do a video later. It's not going to be tonight, but I will do a video later on more complicated systems, because what happens if you have, if you do x, y, z, x, y, z, x, y, z, oh my gosh, how are you going to solve that, right? You have the tools, but in case you're stuck, in case you're struggling, I'll have some examples up for you to reference, okay? And overall, just have a good night. Enjoy the evening or the morning or whenever you're watching this, and take care. I say goodbye.